In this lesson, we're going to be looking at the derivatives of trigonometric functions. Now, when we're working with trig functions in calculus, we need to be in radians and not degrees. So make sure when you're working with your calculator, set the mode to radians unless you have a problem specifically saying that we are in degrees. You're going to change it to degrees, but I leave mine in radians at all times until I see a problem that needs to be switched to degrees. All right, let's take a look at a function here. This is the graph of the sine function, and we're going to try to determine what is the derivative of the sine function. Let's take a look at the slope of the tangent lines and see if we could graph the derivative function to the sine graph here. So I'm going to choose this value here. First of all, it looks like 1.5 or so, and draw in the tangent line. It looks like the slope of the tangent line would be 0 there. So I'm going to plot a point. This would be a point on the derivative graph. And if I did that, every place that I saw the slope of the tangent line equals 0, I'll plot a point there. Slope of the tangent line here, it looks like is 0. So I'm just plotting points wherever it looks like the derivative graph is 0. And then we have one over here, it appears. Okay. Now let's look at what's going on between those points. So I'm going to start with this point here, where x equals, looks like about negative 1.5. And if we analyze the graph a little bit more, we would see that's negative 1.57 or negative pi by 2. We can see the graph as the values of x started getting closer to 0. The slope of the tangent lines here, we're looking at the slope of the tangent lines here, they're getting more positive. Now, at 0 is where the slope of the tangent line is the greatest. It has the greatest positive value. And if we calculated the slope of that line, it looks like it's about 1. So I'm going to plot a point up here at 1. Now I know the values from this negative pi by 2 and up to x equals 0, they're becoming more and more positive. So I'm just going to draw the graph there. And then as we let x get larger, you can see the slope of the tangent lines are getting less positive, and they're starting to get closer and closer to 0 at this point here. So our graph would come back down here through that point. Now, continuing letting x get larger, we can see now the slope of the tangent lines become negative. So we're going to be below the x-axis, and it appears the line would be most negative, the tangent line, about here. And if we calculated the slope of the tangent line there, it appears to be negative 1. So our graph would approach that value there. And as x got larger, you can see the slope of the tangent lines are becoming less negative until we hit 0 again at this point. The slope of the tangent line there would be 0. So we're going back up to this point. And if we repeated this process, we can see I'm again saying the slope of the tangent line here is at its greatest, and it appears to be 1. So we would put it up here. And so we would have this. And if we did the same analysis over here, we would see this. And so here would be the greatest value, 1, and we'd come back down. So we have our y equals the sine of x. That's the original function. And we have just now graphed the derivative of the sine function. And that should look familiar. That looks like it's the cosine curve. So we're thinking that the derivative of sine is cosine. That's looking at it graphically. Here we have the derivative, the function and its derivative. Let's try to confirm that indeed the derivative of the sine function is the cosine function. We looked at it graphically. It looks like it is cosine. Let's try to do it analytically now. So we're going to go back to our limits and see if we can determine the derivative of the sine of x using our limits. Our function is the sine of x, so every place we see an x, we're going to plug in an x plus h, so we'd have the sine of x plus h minus f of x, our function is sine of x, divided by h. We're taking the limit as h goes to 0. That's the definition of a derivative. Now thinking back to our trig rules, we know that the sine of one angle plus another angle is the sine of the first times the cosine of the second plus the cosine of the first sine of the second. And then we have minus sine x. And if we tried to plug in 0, we can see we would get 0 over 0. So let's try to rewrite this somehow so we can use direct substitution. Let's group together our sine x's, so maybe we could factor that out. So we took the end term, the minus sine of x, and we grouped it with our sine x times cosine of h. So now we could factor that out. So if we took the limit, we know properties of limits, we can take the limit of each one of these independently. If we took the limit of each one of these, well, we could use direct substitution for a couple of these, but the others, well, there's one of them that we may have to do a little exploration. Now, the limit of the sine of x as h goes to 0. That is just going to be the sine of x, because the sine of x doesn't have an h in it, so it's considered a constant. So the limit of a constant as h goes to 0 is just that constant. So we would just get the sine of x. Let's skip over the second limit for a moment. Now, what's the limit of cosine of x as h goes to 0? Well, that would be just cosine of x. And the last limit, that's one of the special limits we looked at using the squeeze theorem. So we know that limit equals 1. So let's see if we can find this limit of the cosine of h minus 1 divided by h as h goes to 0. If we use direct substitution, we would get 0 over 0. So we're going to have to try one of the techniques we've learned. So let's multiply by the conjugate of the numerator. Now, in the numerator, we would get a cosine squared h minus 1. And if you use the rule sine squared x plus cosine squared x equals 1 and manipulated that algebraically, you would see cosine squared h minus 1 is equivalent to negative sine squared h. Now we can break that up. We can bolt a negative out front of the limit, and then the sine squared h we can rewrite as sine of h over h times the sine of h over cosine of h plus 1. Now we know that the limit of the sine of h over h as h goes to 0, we know that limit. That's just 1. Now what about the limit of the sine of h divided by cosine of h plus 1? Well, that one, if we use direct substitution, we would get sine of 0, which is 0, divided by cosine of 0, which is 1 plus 1. So we'd have negative 1 times 0, which is just 0. So that quantity, that limit, goes to 0. So we have sine of x times 0 plus cosine of x times 1, which is just cosine of x. So that verifies what we found graphically. The derivative of the sine of x is the cosine of x. Differentiate y equals x squared times the sine of x. We have an f of x times a g of x, so we need to apply the product rule. We'd have the first function times the derivative of the second function plus the second function times the derivative of the first function. We just found the derivative of the sine of x is cosine, and the derivative of x squared is just 2x. So we'd end up with x squared times cosine of x plus 2x times the sine of x. That's our derivative. Find the derivative of the cosine of x. We're going to have to go back to our limits, and just like we did with the sine of x, see if we can use our limits to find this derivative. And it's kind of the same process. You'll see we're going to have to regroup in the numerator so we can factor out the cosine of x. And then we'll write the limit for each one of those. And again, the limit of the cosine of x as h goes to 0, just cosine of x. And these others, we have found that in the last slide, the limit of cosine of h minus 1 over h as h goes to 0, we found that to be 0. And then we have a minus the limit of the sine of x as h goes to 0. We know that's the sine of x times the limit of the sine of h over h as h goes to 0. We know that's 1. So we get negative sine of x. So we have found the derivative of the cosine of x is negative sine of x. You should be able to recreate this process, finding the derivative of cosine using limits. So just give it a try on your own, and if you get stuck any place, you can refer back to the video. But try to find the derivative of cosine x using limits. Find the derivative of the tangent of x. We're not going to use limits for this one. We're going to be a little bit more creative. We're going to change the tangent of x into sine of x divided by cosine of x, and then use the quotient rule. The quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And now we know the derivative of sine x, we know the derivative of cosine of x. Now notice in the numerator we get cosine squared x plus sine squared x. That looks familiar. Thinking about our trig functions, that's a Pythagorean identity, and so cosine of x plus sine squared of x equals 1. So we could change that to 1. So we'd have 1 over the cosine squared x, and then we know that 1 over cosine squared of x equals secant squared of x. So the derivative of tangent of x is secant squared x. We went through and found the derivative of sine, cosine, and tangent. You could do the same thing with cosecant, secant, and cotangent. But here are the derivatives of all 6 of our trigonometric functions. Differentiate the secant of x divided by 1 plus tangent of x. For what values of x does the graph of f have a horizontal tangent? Let's discuss both of these independently. If we're trying to differentiate f of x, it appears we're going to have to use the quotient rule. Now it says, for what values of x does the graph of f have a horizontal tangent? So the slope of the tangent line would equal 0. So if we set the derivative equal to 0 and solved for x, we should be able to find for what values of x does the graph of f have a horizontal tangent. So we formulated our plan. So finding the derivative, first of all, we have the bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared. And you can verify that the derivative of secant x and the derivative of 1 plus tangent x and we're going to factor out a secant x, and within this brackets, within these brackets, here again we have a Pythagorean identity. We have tangent squared x plus 1 equals secant squared x. So if we want tangent squared x minus secant squared x, we would have to take subtract 1 from each side. So we could change that to minus 1. So you see where that came from. So we have our derivative. Now, where does a rational expression, where does the secant of x times tangent of x minus 1 divided by 1 plus tangent of x squared, where does that equal 1? Well, where the numerator equals 0. So we could set the numerator equal to 0. And when we set the numerator equal to 0, we have two factors, so we'd have to set each factor equal to 0. Here we'd get tangent of x equals 1. So those are the values of x where tangent of x minus 1 equals 0. Now for secant x, that never equals 0. So that will not give us any solutions. So we have found the derivative, and we found what values of x does the graph of f have a horizontal tangent. An object at the end of a vertical spring is stretched 4 centimeters beyond its rest position and released at time t equals 0. Its position at time t is, so we have a position function, f of t equals 4 cosine of t. Find the velocity at time t and use it to analyze the motion of the object. If we have a position function, f of t, we know the velocity function comes from finding the derivative of our position function. We know how to find the derivative of 4 cosine of t. The 4 is just a coefficient. We can bring that out front. The derivative of cosine t is negative sine t. So our derivative, or our velocity function, would be negative 4 times sine of t. The amplitude is from negative 4 to 4. The amplitude is actually 4. And the period is 2 pi. If we looked at the position function and the velocity function on the same graph, we could do a little bit more analysis here. There's the function and the derivative function. What can you say about the velocity of the spring at x equals 0. Here, the purple graph is our position function. We have a line when x equals 0 indicating that's the tangent line, and we can see the slope of the tangent line when x equals 0 to our graph is 0. Now look at the derivative graph, the white graph. We can see the value of the derivative function when x equals 0 is 0. Where is the speed the greatest? We're looking for where the velocity graph has the greatest value. So at 0, do you see the velocity graph? I'm sorry, I was looking at the pink graph. That's the position function. Now at negative pi by 2, do you see the velocity graph has a value of 4? And then go to pi by 2, which is about 1.57. And do you see we have a value of negative 4? So speed comes from the absolute value of the velocity. So at negative 4, the absolute value is 4. So at the peaks and valleys of our velocity function is where we have the greatest speed. And you can do further analysis on this, which is interesting. You could look at what's happening with the position function and compare it to the velocity function. And think about what's going on. You've pulled a spring, it's oscillating up and down, and you can look at the position and the velocities. Find the limit of the sine of 7x divided by 4x as x approaches 0. We've done a problem similar to this previously. We know that if we could get our argument for the sine of 7x, our argument is 7x. If we could get a 7x in the denominator also, we know the limit of the sine of 7x over 7x as x approaches 0 equals 1. So let's use a substitution. Let's let u equal 7x. So we could rewrite by multiplying u by 4 over 7. We could get 4 over 7 times u equals 4x. So we would have 7/4 times the limit. Now remember, when you use a new variable, you have to replace everything in terms of u, and also you have to replace, as x goes to 0, you have to say, well, where is u going to? And you can use, when you do that, look back at your substitution. Here, as x is going to 0, where is u going to? Or you can use this one. As x is going to 0, well, u would be going to 0. Now, in terms of u, we can see the limit of the sine of u divided by u as u goes to 0. That equals 1. So we get 7/4 times 1 gives us 7/4. Calculate the limit of x times the cotangent of x as x approaches 0. Let's rewrite cotangent in terms of sine and cosine. Now we could rewrite this as the cosine of x divided by the sine of x divided by x. We would have the limit of the cosine of x as x approaches 0 we would have in the denominator the limit of the sine of x divided by x as x approaches 0. And in the numerator, we could use direct substitution. And in the denominator, we can see that limit equals 1.